Very good afternoon, everyone. So, we were looking into the various classifications, definitions, properties, characteristics of partial differential equations in the last class, and at the end of the last class we defined a linear operator, and we have looked into the property of the linear operator, that if the operator is linear, we can use the principle of linear superposition. We have demonstrated one example in the case of ordinary differential equation to explain the use and application of principle of linear superposition. In that case, if you remember whatever we have done, we took up a problem of second order, which will be having where they will be having two boundary conditions to solve the problems, and the both the boundary conditions were non-homogeneous and the governing equation was also non-homogeneous. So, there were three sources of non-homogeneity in the problem. So, we divided the problem into three sub-problem, considering one non-homogeneity at a time and forcing the other two non-homogeneities to vanish. Then we took up each and individual problem. So, we took up each of the three problems. Each of these three problems will be containing only one non-homogeneity at a time now. Now, we solved these three problems separately and added the solution up in order to get the overall solution. So, that simplifies the whole problem. So, it may not be apparent to you what is the benefit of this method of principle of linear superposition by solving the ordinary differential equation, but it will be quite apparent to the advantage will be quite apparent for in the case of solution of partial differential equation. In case of ordinary differential equation, it was taken up as for demonstration purpose. For the case of partial differential equation, the advantage will be quite apparent. So, in this class we will be taking up an example to demonstrate the principle of linear superposition in case of partial solution of the partial differential equation, and how that will help in overall solution. We will just look into that. So, we look into the application of principle of linear superposition. Consider a second order general partial differential equation . Let us say grad square u is equal to b del u del t plus a u plus c del square u del t square minus f, say function of x, y, z and t in general. So, we are considering a 4-dimensional problem where x, y, z are the 3-dimensional main spatial dimensions, and t is the time dimension. So, it is a 4-dimensional problem. Grad square is a generalized Laplacian operator. So, this will be del square del x square plus del square del y square plus del square del z square. So, in this equation, let us say this is equation number 1. In equation number 1, what we have? We have if b is not equal to 0 and c is equal to 0, we will be getting a parabolic PDE. If b is equal to 0 and c is equal to 0, then we will be getting an elliptic partial differential equation. For C greater than 0, we will be getting hyperbolic partial differential equation. If f is equal to 0, we will be getting a homogeneous partial differential equation. Now, general boundary condition will be it will be alpha del u del n, n is basically the normal direction of any surface, beta u is equal to h. So, that is a general boundary condition on any boundary. If h is equal to 0, we will be getting a homogeneous boundary condition. If alpha is equal to 0, we will be getting a non-homogeneous Dirichlet boundary condition. If beta equal to 0, then you will be getting non-homogeneous Neumann boundary condition. If none of them will be, if the equation A as it is, then that is equation A is a Robin mixed, but non-homogeneous boundary condition. Now, we like to use principle of linear superposition to simplify this partial differential equation. So, what we will do? Let us write down grad square u is equal to a u plus b del u del t minus f is the non-homogeneous equation. Let us say this is non-homogeneous parabolic partial differential equation. So, you will be initial condition. So, let us consider this one. Initial condition will be, let us say u is some generalized some function of x, y, z. It is a function of space, and the boundary condition is given as alpha del u del n plus beta u is equal to h. N is the normal direction on the boundary of the boundary whatever we are talking about. So, it is basically normal derivative with respect to the boundary. So, let us identify what are the sources of non-homogeneity to this equation. There are 3 sources of non-homogeneity to this equation. This is source number 1. So, this non-homogeneity is appearing in the main governing equation. Then in the initial condition there is another non-homogeneity is present, and in the boundary condition there is another non-homogeneity is present. So, there are 3 sources of non-homogeneity in the problem. So, whenever a differential problem is defined including the governing equation and the boundary conditions, whenever we are talking about a governing equation, it is valid throughout the whole volume of the control volume, and whenever we are talking about the boundary conditions, they will be valid only on the boundary. Therefore, the solution of the differential equation must satisfy the governing equation as well as the boundary conditions. On the other hand, the boundary conditions need not to be solution boundary conditions are valid only on the boundaries, but the governing equation is valid throughout the whole control volume of the system. Now, since there are three sources of non-homogeneity, in this problem, we divide this problem into three parts. So, we divide this problem into three solutions, u is equal to u1 plus u2 plus u3. Since the operator we are talking about is, what is the operator in this problem? The operator will be, so del square u. So, we will take a diversion here and talk about the operator once again. Del square u is equal to a u plus b del u del t minus f. So, so it can be cast in the form L u is equal to minus f. So, L is the operator and this operator is grad square minus b del del t minus a. So, the operator is nothing but del square del x square plus del square del y square minus b del del t minus a. If it is three dimensional space, then one more del square del z square will be appearing here. So, since this operator is a linear operator, we can simply linearly superpose all the three solution and get the complete solution. Now, what will be the solution for what will be the governing equations for this particular sub problems? So, we divide the problems into three sub problems, then u1, u2 and u3 each are called sub problems. So, we define each such sub problems such that we will be considering only one non-homogeneity at a time. Now, how these sub problems will be the governing equation of the sub problems will be formulated. Since this operator is a linear operator, what we will be doing is that we will be substituting u is equal to u1 plus u2 plus u3 in the governing equation. So, if you do that, we will be getting grad square u1 plus u2 plus u3 is equal to a u1 plus u2 plus u3 plus b del del t of u1 plus u2 plus u3 minus f. So, if since the individual parts of these are linear, so it will be getting grad square u1 plus grad square u2 plus grad square u3 is equal to a u1 plus a u2 plus a u3 plus b del u1 del t plus b del u2 del t plus b del u3 del t minus f. Now, what we will be doing, we just, since this operator is a linear operator, we just consider the u1 containing part equal, u2 containing part equal and u3 containing part equal. We separate them out, and while separating we put f into one f, we associate the non-homogeneous term f along with the any of the sub problems u1, u2, u3. Let us say we associate f with u3, we could have associated f with u1 as well. So, if we compare the u1 containing part, u2 containing part and u3 containing part from this equation and make the separate sub problems from them, what we will be getting? We will be getting the governing equation of individual sub problems. So, let us first construct the governing equation of u1. Take out the u1 containing part. So, grad square u1 is equal to a u1 plus b del u1 del t. Okay. Similarly, the governing equation of u2 will be grad square u 2 is equal to a u 2 plus b del u 2 del t, and u 3 will be nothing but grad square u 3 is equal to a u 3 plus b del u 3 del t plus minus f. So, we associate the non-homogeneous term f with the third sub problem. If you add these three up linearly, then you will be getting the original problem, the governing equation of the original problem u. So, once we get that, now let us look into the boundary conditions as well. So, if you look into the initial condition of the original problem, the initial condition of the original problem was g u is equal to g x y z. So, therefore, you just write u is equal to u 1 plus u 2 plus u 3 is equal to g. So, therefore, the initial condition can be for each of them can be written down as u is equal to g for the u 1 is equal to g for the first sub problem, u 1 u 2 is equal to 0 and u 3 is equal to 0. So, this is the initial condition of the first sub problem, this is the initial condition of the second sub problem, this is the initial condition of the third sub problem. If you look into the boundary condition of the original problem was alpha del u del n plus beta u is equal to h. So, if you put u 1, u 2, u 3 in the place of u, then you will be getting del u 1 del n plus alpha del u 2 del n plus alpha del u 3 del n plus beta u 1 plus beta u 2 plus beta u 3 is equal to h. Again, we take up the u 1 containing part, u 2 containing part, collect the u 1 containing, u 2 containing, u 3 containing part separately and associate h with the appropriate problem, and we will be getting the boundary condition of each sub problem. So, if we take alpha del u 1 del n plus is equal plus beta 1 u 1 is equal to 0. So, that is the boundary condition for u 1. Then similarly, what we will be getting alpha del u 2 del n plus beta u 2 is equal to h, that is the boundary condition for u 2. So, here you just note we associated the non-homogeneous part h in the boundary condition with the solution with the sub problem u 2, because we want to have each sub problem will be containing only one non-homogeneity at a time. So, we could have associated h with u 1 or with u 3, but u 1 is already having one non-homogeneity, that is in the initial condition. So, we did not associate the non-homogeneous term of h in the along with u 1. On the other hand, in case of u 3, if you remember, u 3 contains, we associated the non-homogeneous term of the governing equation in u 3. So, therefore, u 3 is already containing one non-homogeneous term. So, we intentionally did not associate the boundary condition non-homogeneity of the boundary condition with u 3, simply because u 3 must be having only one non-homogeneous term either in the governing equation or in the boundary. So, the only choice left is association of non-homogeneous term of the boundary condition with u 2, so that u 2 will be having only one non-homogeneity in the form of this boundary. So, alpha del u 3 del n plus beta u 3 is equal to 0 is the boundary condition for u 3. So, if we look into the three sub problems, now u 1 is having a governing equation grad square u 1 is equal to a u 1 plus b del u 1 del t. The initial condition is u 1 is equal to g, boundary condition is u 1 alpha del u 1 del n plus beta u1 is equal to 0. For this is for u1, for u2 grad square u2 is equal to a u2 plus b del u2 del t, and initial condition is u2 is equal to 0 and boundary condition is alpha del u2 del n plus beta u2 is equal to h. This is the one, and we will be writing down for u3. u3 is governing equation is grad square u3 is equal to a u3 plus b del u3 del t, and the initial condition is u3 is equal to 0 minus f was there, u3 equal to 0 and alpha del u3 del n plus beta u3 is equal to 0, that comes from this. So, this is the boundary condition for the third sub problem. Now, if you closely examine each of these sub problems, that you will be having only one non-homogeneity in this formulation, you will be having only one non-homogeneity in this equation. In this problem, each of these sub problems will be having only one non-homogeneity in them. In this case, first case u1 g is the non-homogeneous term, in the second case h is the non-homogeneous term, in the third case governing equation f is the non-homogeneous term. So, therefore, we will be dividing the problem into three sub problems considering one non-homogeneity at a time, and probably now it must be clear to you how to reconstitute or reformulate each of the sub problem having one non-homogeneity at a time. So, you should have a judicious selection of association of the non-homogeneous term in the boundary conditions as well as in the governing equation to the appropriate such sub problem, such that that particular sub problem under concern will be containing only one non-homogeneity at a time. Now, most probably will be the most common method of solving the second order partial differential equations is use of separation of variables. In case of separation of variables, if you remember that we divide the solution into solution into the two sub parts, and the entire solution is constructed by multiplication of the two parts, and we consider one part is entirely a function of a particular variable, another part is a sole function of the particular variable. Then we multiply these two and construct all the solutions and add them up simply, and we will be getting the complete solution. But in this case, if you remember that if you have the initial condition, so you will be having three conditions in general, two conditions in space, one condition in time, that is known as the initial condition. When you formulate the sub problem, then these two conditions in the space will be used up to get the solution of one of the sub problem, one of the let us say space varying time, space varying solution, and in the time varying solution you will be getting only one condition, that is the initial condition. When you construct the complete solution, so one constant will be evaluated by using the initial condition. So, you will be utilizing all the three conditions. Now, if the initial condition becomes 0, then the whole problem, so the formulation of the partial differential equation becomes an ill-posed problem. So, that cannot be entertained, because if whenever you will be evaluating the solution of the partial differential equation, the final constant will be evaluated from the initial condition, and final constant will be multiplied with the rest of the solution. So, if you put the initial condition as 0, then the whole solution becomes, the whole problem becomes ill-posed problem, ill-defined problem. So, we have to make the problem well posed. Now, if you look into these three sub problems, whatever we have considered, in two cases, the sub problem u2 and sub problem u3, we have the initial condition 0. So, sub problem definition of u2 and u3 are not well posed. On the other hand, the sub problem u1 is well posed, because here it has homogeneous boundary condition and non-homogeneous or non-zero initial condition. So, let us note down whatever we are trying to say, that Illposed partial differential equation is that PDE that contains homogeneous initial condition. Okay. For example, in the sub problem, the initial condition u2 is equal to 0. That means, in a particular problem at time t is equal to 0, u2 is equal to 0. This is Illposed partial differential equation. And which one is Illposed? Illposed PD is the one where the initial condition is non-homogeneous. But boundary conditions are homogeneous. Okay. So, in this case also, if you look into so boundary condition, so initial non-homogeneous initial condition and homogeneous boundary conditions are Illposed partial differential equation. Now, you cannot so this solution is direct. On the other hand, for the Illposed problem, one has to convert the Illposed problem into Illposed problem. So, conversion of Illposed PD to Illposed PD is very important. Now, how this conversion is done? So, let us consider the problem number u2. Both problem u2 and u3 in the current example, they are Illposed because they have homogeneous initial condition or zero initial condition. So, what we have to do? We have to again divide the problem into two sub problems. Problem into two sub problems. Okay. So, u2, so one part will be time dependent and another part will be time independent. So, that will be corresponding to the steady state solution. So, u2 can be broken down into two parts, u2 steady state, which will be a function of space only, and it will be having a transient part or time varying part, which will be function of space as well as time. Now, what we will be doing then we will be again formulating the governing equation and the boundary conditions of the steady state part and the transient part. For that, we take recourse to the same method as we have considered earlier. So, let us look into the what is a parent problem for u2. The mother problem for u2 is grad square u2 is equal to a u2 plus b del u2 del t. So, we write down the u2 is equal to u2s plus u2t. So, grad square u2s plus grad square u2t is equal to a u2s plus a u2t plus b del u2t del t, but when you when you write u2s, okay, we write del u2s del t, but u2s is a sole function of space. It is a function of x, y and z. It is a steady state solution. So, u2s is not a function of x, y, z. So, therefore, the partial derivative with respect to time will be equal to 0. So, this does not exist. So, again we take out we collect the similar terms and formulate the governing equation of u2s. So, what is u2s? the governing equation of U2s is nothing but grad square U2s is equal to A U2s. And what is the governing equation of U2t? U2t will be, just collect the similar terms, grad square U2t is equal to A U2t plus B del U2t del t. Now we have to formulate the initial and the boundary conditions for this problem. Let us look into the initial condition of the original problem of U2. The original problem was U2 is equal to 0. So, we have U2s plus U2t is equal to 0. So, therefore, we do not need an initial condition of on U2s, because U2s is a function of space only, it is not a function of time. So, therefore, we need not to have initial condition on U2s. So, therefore, the initial condition is not appropriate for U2s. So, we write it down here. I think that will be better, because we need to have one initial condition on U2t. So, U2 is equal to 0. So, we have U2t plus U2s is equal to 0. So, U2t is nothing but minus U2s, which will be a function of x, y, z. So, initial condition of the transient problem is nothing but the solution of the steady state part and a minus sign with it. So, we just cut it down here. Now, we get the boundary condition. The boundary condition was for U2 was alpha del U2 del n plus beta U2 is equal to h. So, alpha del U2s del n plus alpha del U2t del n plus beta U2s plus beta U2t is equal to h. Again, collect the similar terms. So, U2 containing term you will be getting alpha del U2t del n plus beta U2t is equal to 0, and we associate the non-homogeneous term with the steady state solution. So, alpha del U2s del n plus beta U2s is equal to h. So, therefore, this is the boundary condition for the steady state part, and this is the boundary condition for the transient part. Now, you just see the steady state part requires only the boundary conditions. So, therefore, with the help of this boundary, steady state part does not require any initial condition, because it is time independent. So, therefore, with the help of this boundary condition, one will be able to solve the steady state part completely. So, this governing equation of the steady state part along with this boundary condition is a complete solution, will lead to a complete solution of U2s as a function of space x, y and z. Once that is known, then we come back to the transient part. In the transient part, this is the transient equation, and initial condition U2 was U2t is nothing but minus of steady state solution. We have already known the steady state solution from here, that will be used as the initial condition of the transient problem. And if you look into the boundary condition of the transient part is completely homogeneous. So, we are having a non-zero, non-homogeneous initial condition, homogeneous boundary condition for the problem U2, and U2t is now has become a well posed problem. So, we have converted U2t in the U2t is a well posed problem from an ill posed problem. So, U2t is now become a very well posed problem. Similarly, we can look into the derivation for U3t. So, let us look into U3. U3 we have already said it is ill posed problem. So, it has a zero initial condition or homogeneous initial condition. So, therefore, we make it into, we break it into two sub problem. Once again, U3 is a function, U3s, that is a function of space x, y and z, that is a steady state part, plus U3t, that will be function of x, y, z and t. Now, we should get the governing equation of U3S and U3T and the relevant boundary conditions and initial condition. So, if you look into the mother problem of U3, grad square U3 is equal to A U3 plus B del U3 del T minus F. So, we just put U3 is equal to U3S plus U3T. So, this becomes grad square U3S plus grad square U3T is equal to A U3S plus A U3T plus B del U3T del T, and del U3S del T will be equal to 0, because U3S is a sole function of x, y, z, it is independent of t minus f. Now, we compute the we separate the steady state part and the transient part and formulate the governing equation of U3S and U3T. So, what is the governing equation of U3S? We collect the similar terms. So, grad square U3S plus A U3S minus grad square U3S is equal to A U3S minus F. So, we intentionally attach the non-homogeneous part with the space varying part or the steady state part, because that will be easier to solve. That will make the partial differential equation in terms of t and space homogeneous. And what is U3T? U3T will be grad square U3T is equal to A U3T plus B del U3T del T, and initial if you look into the initial condition was U3 of the original problem was U3 was equal to 0. So, therefore, U3T plus U3S is equal to 0. Therefore, initial condition is for U3T is nothing but minus of U3S, which is a solution, which is a function of x, y, z, and this is the solution of the steady state part. So, we solve the steady state part completely, and the solution of the steady state part has become the initial condition of the transient part. And now, look into the boundary condition. The boundary condition was alpha del U3 del n plus beta U3 is equal to 0. We put U3 is equal to U3S plus U3T. So, alpha del U3S del n plus alpha del U3T del n plus beta U3S plus beta U3T is equal to 0. Again, we collect the similar terms. So, this boundary condition for the steady state part will be alpha del U3S del n plus beta U3S is equal to 0, and here the boundary condition for U3 will be alpha del U3T del n plus beta U3T is equal to 0. So, if you look into this problem, this is the governing equation of the steady state problem along with this boundary condition. You do not read any initial condition to solve the steady state part, because steady state part is time independent. Now, with the help of these boundary conditions, this steady state equation can be completely solved, and we will be getting U3S as a function of x, y, and z. So, therefore, that solution of the steady state part will be the solution of the will be the initial condition of the transient part. So, we will be knowing it, that will be known to us with a negative sign, of course. And if you look into the boundary condition, the boundary condition has become of transient part becomes homogeneous. So, therefore, if you look into the formulation of these sub problems, one common thing is clear to you, that each of these sub problem will be having only one non-homogeneity at a time. If you look into U3T, the boundary governing equation is homogeneous, the boundary condition is homogeneous, the initial condition is non-homogeneous. So, out of this, in the three sources of the equation, only one non-homogeneity is occurring here. In the case of U3S, the governing equation is non-homogeneous because of the presence of f, the boundary condition is homogeneous, So, there is only one source of non-homogeneity here. Similarly, if you look into the other problems, other sub problems, U2T is having a homogeneous governing equation, a non-homogeneous initial condition and a homogeneous boundary condition. In case of U2S, it is homogeneous governing equation, it is a non-homogeneous boundary condition. So, only one source of non-homogeneity is present there, and in case of U1 it is Illposed problem. So, therefore, in this case the governing equation was non-homogeneous, the initial condition, the governing equation was homogeneous, the initial condition was non-homogeneous and the boundary condition was homogeneous. So, we will be dividing the problem into sub problems considering only one non-homogeneity at a time, and if your initial condition of a transient problem becomes homogeneous, then you are in trouble. You have to break down the problem into two more sub problems such that each sub problems will be containing only one non-homogeneity. So, while you are formulating the governing equation for the sub problems, ensure that association of the non-homogeneous term should be done appropriately. So, therefore, now you will be in a position to get the complete solution of the problem. Complete solution is given as a linear superposition of all the sub problems U1 plus U2 S plus U3T, U2T plus U3S plus U3T. That gives the complete solution, and U2S is the steady state part of the second sub problem, U2T is the transient part of the second sub problem, U3S is the steady state part of the first sub problem, U3T is the transient part of the third sub problem. And by using a linear superposition of all the solutions of the sub problems, one can constitute the complete solution of the original problem. Okay. Next, we will be taking up an example of elliptic partial differential equation, elliptic PDE, and in this case we are writing it the two dimensional Laplacian operator del square del x square plus del square del y square, del square u del x square plus del square u del y square is equal to 0. And in order to solve this problem, you must be having two boundary conditions on x, because it is order 2 with respect to x, two boundary conditions on y because it is order 2 with respect to y. Now, let us define our boundaries like this. This is x axis, this is y axis, this surface is x is equal to 0, this boundary is located at x equal to 0, y equal to 0, this boundary is located at x equal to 1, y is equal to 0, this boundary is located at y is equal to 1 and x is equal to 1. Okay. And so all these four boundaries can be specified. So, since here u is equal to at x is equal to 0, y. So, this is this boundary, here it is defined as the boundary condition is G2, in general it will be function of y. The boundary condition on this plane, on this surface is y equal to 0, and here the boundary condition is u at any x, but at y is equal to 0. This is, let us say, f1, and this boundary is located at x is equal to 1. So, u at x is equal to 1 for any y, this value is g1 y in general, and this is located at y is equal to 1, but any x. So, x is equal to 0, x is any x, and y is equal to 1, u is equal to f2 x. So, that means there are four boundaries, x is equal to located at x equal to 0, x equal to 1, y is equal to 0 and y is equal to 1. At x is equal to 0, you have u is equal to g2 y, at x is equal to 1, you have u is equal to g1y at y is equal to 0, your boundary condition is f1x, and y is equal to 1, your boundary condition is f2x. So, we have, if you look into the problem and its boundary conditions, that this is the governing equation, and this governing equation is homogeneous. There is no non-homogeneous term present into this boundary, this partial differential equation, which is elliptic in nature. On the other hand, it contains the 4 boundaries, and all of these 4 boundaries are non-homogeneous in nature, and therefore, we have to break down this problem into 4 sub problem considering one non-homogeneity at a time. So, what I will do? I will break down this problem into 4 sub problem, u1 plus u2 plus u3 plus u4, and we construct the solution, the governing equation of each sub problem. Okay. u1 will be del square u1 del x square plus del square u1 del y square is equal to 0, and you just put u1 is equal to at x equal to 0, u1 is equal to g2y, and u1 at x is equal to 1, u1 is equal to 0, at y is equal to 0 and 1, we put u1 is equal to 0. So, we are keeping only one non-homogeneity at a time, forcing the other 3 non-homogeneities to be 0. That gives the construction of the governing equation of first sub problem. Then we look into the governing equation and the boundary condition of the second sub problem. This will be del square u2 del x square plus del square u2 del y square is equal to 0. So, at x is equal to 0, we consider u2 is equal to 0, we have the other boundary condition, a non-homogeneous boundary condition to be intact. So, u2 is equal to g1 y, and other 2 boundary conditions at y is equal to 0 and 1, we have, let us say, u2 equal to 0. So, therefore, we keep one non-homogeneity here, forcing the other 3 non-homogenities to be 0, and we formulate the governing equation of u3 del square u3 del x square plus del square u3 del y square to be equal to 0, and boundary conditions at x is equal to 0 and 1, we have u3 equal to 0, y is equal to 0, we keep this non-homogeneity u3 is equal to f1x, and y is equal to 1, we force the non-homogeneity to vanish. So, therefore, we keep the boundary condition at y equal to 0, that non-homogeneity we keep intact and forcing the other 3 non-homogenities to vanish. Therefore, we can formulate similarly the 4th sub problem u4 del square u4 del x square plus del square u4 del y square is equal to 0, at x equal to 0 and 1, u4 is equal to 0, and at y is equal to 0, we force the non-homogeneity to vanish, and at y is equal to 1, we keep that non-homogeneity to be intact, and that will be u4 is equal to f2x. So, that completes the 4th sub problem, and if you look into each of these sub problem, that only in problem number 1, only one non-homogeneity is kept intact, that is at boundary x is equal to 0. In problem number 2, only one non-homogeneity is kept intact, that is given in problem on the boundary condition located at x is equal to 1. In the 3rd sub problem, only one non-homogeneity is kept intact, that is the boundary located at y is equal to 0, and in the 4th problem, we kept intact only one non-homogeneity, that is the boundary condition located at y is equal to 1. So, each of these sub problem is well posed, and we will be able to solve them quite elegantly without any hassle. So, that is important, we keep only one non-homogeneity at a time, force the other all non-homogeneities to vanish, so that we can make a problem well posed, and that well posed problem will be easier to solve. Okay. So, next we will be look into a particular special solution of a special type of ordinary differential equation. Okay. So, that is how we will be using the principle of linear superposition for bringing down, for resolving the partial differential equation into subparts. So, that every subpart contains only one non-homogeneity at a time, and each of these subproblem is a well defined problem. So, now this point onwards we will take a diversion and look into special type of ordinary differential equations, and later on we will connect this type of ordinary differential equations, how they will be relevant to the solution of partial differential equation. Okay. Consider a second order ODE of the form d square y dx square plus lambda y is equal to 0, subject to conditions at x is equal to 0, y is equal to 0, and at x is equal to 1, y is equal to 0. Now, this type of equations, this is a special type of equation where where lambda is a scalar. Scalar in this case, in case of continuous function, scalar indicates it is a constant. Okay. So, at x is equal to 0, both the, if you look into the nature of this equation, you will be having, you can see that this equation is a homogeneous equation. So, it is not non-homogeneous. On the other hand, the boundary conditions are both homogeneous. So, therefore, this is a set of homogeneous equation as well as the homogeneous boundary condition. So, this equation is known as a standard eigenvalue problem. It has also a special name, that is called a Sturm-Liouville problem, and Sturm-Liouville problem. But please note that this is not a general equation for a standard eigenvalue problem. This is a special case of generalized, this is a special case of Sturm-Liouville problem or a standard eigenvalue problem, and this is also a standard eigenvalue problem. We will be looking into more generalized version of the standard eigenvalue problem and Sturm-Liouville problem in the next class, but probably before that we should look into the solution of this equation. So, one obvious solution is that if y is equal to 0, it satisfies the governing equation as well as the boundary condition. So, the solution y is equal to 0 satisfies the governing equation as well as the boundary conditions. So, 0 is a solution. So, y is equal to 0 is a solution, but this is an obvious solution. So, therefore, this particular solution is known as the trivial solution. On the other hand, we are not looking into the trivial solution, we are looking into the specific meaningful solution. So, therefore, in the next class we will be looking into how the meaningful solutions or the non-trivial solutions will be obtained from the standard eigenvalue solution, standard eigenvalue problem like this, and how one can get different kind of solutions by changing the boundary conditions. So, we stop in this class. At this point, we will look into more detail of the standard eigenvalue problem in the next class. Thank you very much.